All right, let's dive in. Today, we're going to crack a classic computer science puzzle. It's a fantastic way to get our heads around a super powerful technique called dynamic programming. And our mission, should we choose to accept it, is to find the longest palindromic subsequence that's hiding inside any given string. You ready? Let's do this.
So to get our brains warmed up, let me ask you something. What in the world do race car and the string BBBBA have in common? I mean, race cars is perfect, elegant, symmetrical word, right? And BBBBA, well, it's kind of just a jumble of letters. But trust me, there's a secret connection hiding in plain sight, and together we are going to find it.
Okay, before we really get into the weeds, let's just quickly make sure we're all speaking the same language. Two key ideas here. First, a palindrome. You probably know this one. It's just a sequence that reads the same forwards and backwards, like level, simple. Now, the second one, subsequence, is a little more interesting. It's what you get if you take a string and just delete some characters, maybe none at all, without messing up the order of what's left. So, for example, ACE is a subsequence of A, B, C, D, E. Makes sense, right?
All right, so let's mash those two ideas together. That's our puzzle for today. We get a string, any string, and our job is to find the length of the longest subsequence we can find inside it that also happens to be a palindrome. So for our friend Bibby Bob, the answer is actually 4. Why? Because you can pull out BBBB. Pretty cool, huh? The real question is, how do we build an algorithm that can figure this out for any string we throw at it?
Section 1. Breaking down the problem. So, how do you eat an elephant? One bite at a time, right? It's the same with these kinds of problems. The secret sauce is always breaking it down into smaller, way more manageable pieces. And our whole strategy is going to revolve around this simple idea, looking at the string from the outside in.
Let's grab our example string again, BBBay. Okay, so the first thing we're going to do is look at the two ends, the very first character and the very last one. That's it. This one simple comparison is the bedrock of our whole solution. And from here, we can only go down one of two paths.
So let's think about it. Path number 1, what if those end characters match? What do you think that means for us? Well, it's actually the best possible thing that could happen.
If they match, boom! That's awesome! We've just found two pieces of our palindrome, the bookends. We can lock those in, and that immediately adds 2 to our length. And now check this out. The problem gets smaller. We just have to solve the exact same problem, but for the leftover string in the middle. This is it. This is the recursive magic. We're breaking a big problem down into a smaller version of itself.
But of course, life isn't always that easy, right? So what happens if the ends don't match? Now we've got a bit of a dilemma. We obviously can't use both of them in our palindrome, so we have to make a choice.
Yeah, let's look at a new string, say CBBD. The C on one end and the D on the other, they definitely don't match. So they can't both be part of our final answer. So what do? Do we ditch the C and see what the best we can do with BBD is? Or do we ditch the D and try our luck with CBB? The thing is, we have to check out both options.
And the best part is, we don't have to guess which one is better. That's the beauty of this whole approach. We don't guess, we just explore both. We go down both paths, find the longest palindrome we can get from each of those smaller strings, and then we just take the maximum of the two. We let the algorithm find the best path for us.
Section 2, the core recurrence. Okay, so we've got the gut feeling for how this works, right? We've explored the logic intuitively. Now it's time to get a little more formal and turn that logic into a powerful rule, what's called a recurrence relation. Think of this as the engine that's going to drive our whole solution.
So first, a little bit of notation to make our lives easier. Let's say f of ij is our answer. It just means the length of the longest palindromic subsequence you can find in the part of the string that starts at index I and ends at index j. And boom, here it is. This is everything we just talked about, but written down as a clean formula. If the characters at the ends match, our answer is simply 2 for those two characters, plus whatever the answer is for the string squished in the middle. And if they don't match, well, we just take the best of our two options. Either we ignore the first character or we ignore the last one. We take the max. That's it. This little formula is the heart and soul of the entire thing.
Section 3, visualizing the solution. Okay, theory is one thing, but seeing it work is another. Let's actually put this formula to the test. We're going to build what's called a DP table, a solution table step by step, and you'll see how all the pieces just click into place. This is where it gets really cool.
All right, so we're solving for B-Baba. We start with this grid, which is going to hold the answers for every possible substring. And the first thing we do is handle the easiest cases, what we call the base cases. I mean, what's the longest palindromic subsequence of just a single character? Well, it's the character itself, right? Length 1. so we can go ahead and fill the whole diagonal of our table with ones. Easy peasy. Next up, let's look at all the substrings that are 2 characters long. Take BB at the beginning. The characters match, so our formula kicks in. It's 2 plus the answer for the bit in the middle. But there's nothing in the middle, so the answer is just 2. Now, what about something like ba? The ends don't match, so we take the max of the answer for B and the answer for A. We already know from our diagonal that both are 1, so the max is 1. And we just repeat this logic all the way down for all the length 2 substrings.
Okay, now for substrings of length 3. This is where you really start to see the power. Let's take BBB at the start. The ends match, right? Both are B. So the formula says the answer is 2, plus the solution for the character in the middle, which is B at index 1. And hey, we've already solved that one. We just look it up in our table, the answer for B is 1. So 2 plus 1 gives us 3. You see that? We're not recalculating anything. We're building on top of the work we've already done. That's dynamic programming in a nutshell.
And we just keep going like this, working our way up diagonally, filling in the table for substrings of length 4, and then finally length 5. We get to that very last cell, the top right corner, which represents the whole string, BBBA. The ends match, B and B, so we know the answer is 2 plus the solution for the inner string, BBA. We just looked that up in our table. It's 2. So 2 plus 2 gets us our final answer. 4. And there it is. The length of the longest palindromic subsequence in BBBBA is 4. That hidden BBBB we talked about at the beginning. Puzzle solved.
Section 4, the final blueprint. All right, we've seen the theory and we've watched it in action. So let's just boil it all down into a simple step-by-step blueprint you can use to solve this problem anytime.
It really comes down to just 4 steps. 1. You make a grid. 2. You fill in the diagonal with ones. Those are your easy base cases. 3. You just iterate. You fill out the rest of the table using that recurrence relation we came up with, always building on previous answers. And 4. Your final answer is just waiting for you in that top right corner. That's the whole recipe.
So what's the big picture here? The technique is called dynamic programming. And yeah, if you're into the nitty-gritty, because we're filling out a grid, the time and space complexity are both O of n squared. But forget the jargon for a second. The real takeaway, the big idea, is incredibly elegant. You solve a massive problem by breaking it into smaller pieces and then cleverly reusing the answers to those small pieces. Don't solve the same thing twice. That's it.
And that pretty much wraps it up. We figured out how to find the length. But I want to leave you with one more challenge to chew on. How would you change this process to not just get the number 4, but to actually spit out the string BBB itself? Think about it. Everything you need to know is right there in the table we just built. The path is there, you just have to trace it back. Anyway, that's all for now.